Okay. Yeah, we are approaching the end of the semester. About the next few days, my schedule is today. I want to finish section 9.4. On Monday, we still have class on Monday. On Monday, I plan to briefly introduce the Krylov subspace methods. Okay. Then next Wednesday and Friday, we don't have classes. About the final exam, I will email you the time, the location, and the topics covered in the final exam. Final exam should be comprehensive, but final exam will not cover numerical linear algebra because I didn't assign any homework to numerical linear algebra. So final exam doesn't cover numerical linear algebra. Okay. Let me email you what sections the final exam will cover and the time and the location. Monday, we still have class. I introduce you Krylov subspace methods. Yeah, the most popular methods for the solution of large and sparse linear systems. Okay. All right. Today's three topics. Jacobi method, then Gauss-Seidel methods. Gauss-Seidel methods is an improved version of Jacobi method. And the third topic, successive over relaxation method. This method include Jacobi, Gauss-Seidel as special cases. Okay, why the method name successive over relaxation method? I don't know, actually. I don't know. Yeah, the author create this method and he has the right to give any name to his method. Okay, so he called his method successive over relaxation. Okay, take a review about the methods of this time. Okay, yeah, we call matrix T iteration method and U0 initial guess to a linear system, the solution of a linear system. The convergence of this iterative method depends on this theorem. Let this be a natural matrix law, okay, not other matrix law. Yeah, natural, okay, this is important. Yeah, to prove the results in this theorem, we require some properties about a natural matrix law. If iteration matrix T is long, less than 1, then iterative method, I call this equation number 1. Iterative method number 1 will converge to some vector U, starting with any initial guess. Maybe this U depends on U0, maybe. Okay. Yeah, different U0 initial guesses. This equation may converge to different U. Possible. And also the error, the cave iterate UK minus this U, the distance less than this is an upper bound. Okay, less than this number, okay, because t, the norm, less than 1, guarantee UK, the error decrease to 0. Okay, this is a part A. Part B, the result is stronger because here just upper bound, but here roughly an equation. Okay, equation. Okay. Part B says that the iterative method converges to some vector with any in any, okay, any, this is important, any initial guess. This method converges if and only if spectral radius of the iteration matrix T less than 1. Spectral is the maximum of compute eigenvalues, all the eigenvalues of T, then take absolute value on each eigenvalue, then take maximum. The maximum is called spectral radius. Moreover, when spectral radius less than 1, then we have roughly this equation. Okay, roughly this equation. Here, n is a physical number. It is the size of matrix T. K, iteration number. It can go to infinity. Okay, go to infinity. Yeah. So part B, the result, stronger than this. Okay, stronger than this. Okay. This is a review 1. Now, review 2. Jacobi method. How to derive Jacobi method? Okay. Yeah, we want to solve this linear system. Solve, say, the first equation for x1. Solve the second equation for x2, and so on. Solve the ith equation, then we get xi. The right side of this equation, low xi, because the xi now is on the left side, so low xi. This number are denoted by ti1, and this number ti2, and so on. Then we have a fixed point equation, right? Fixed point equation. Replace the x on the left side by uk plus 1. The x on the right side by uk. Then this equation, this iterative scheme is called Jacobi method. A second way to derive Jacobi method is splitting the coefficient matrix of the linear system A. Yeah, here. A second approach to derive Jacobi method. Okay, a split matrix A as strictly lower triangular part of the matrix A plus diagonal part of the matrix A, and then strictly upper triangular part of matrix A. Then the linear system is L D U X is equal to B. Now, rewrite this equation as dx plus L plus U x is equal to B. Then move the second term to the right side, and then move diagonal matrix D to the right side. Then we have this equation. A plus D inverse D B. Okay, yeah. This is a let me call this matrix a T X, and this vector C. Yeah. Now replace the X on the left side, Jacobi method. Replace the X on the left side by U. K plus 1. The right side by U K plus C. Hey, now a natural question is how to know Jacobi method converge with any initial guess. You can base on this field, okay? Based on this field, yeah. Based on this field, yeah. You can compare a peg, a lateral matrix norm, then compare the norm of the iteration matrix. If the iteration matrix, the norm less than 0, guarantee converge to some U. Here, I don't say that this U is the solution of the linear system. This theorem, no guarantee this U is the solution of linear system. Okay, yeah. Also, you can compare the spectral radius of the matrix T. If the spectral matrix, spectral radius less than 1, then guarantee to converge. But compare spectral radius is in practice almost impossible, okay, to get the spectral radius, because first, T, the size is huge. Second, compare all the eigenvalues are very time consuming. Okay, so compute spectral radius is not a practical way to get to know Jacobi converges or not. Okay, but about the convergence of Jacobi method, actually we have a more handy figure. Okay, more handy figure. Yeah, let me present this figure. Yeah, we are solve a linear system. Okay, solve a linear system. Solve a linear system. And then from this linear system, we construct Jacobi method. If the coefficient matrix is strictly diagonally dominant. What do you mean? Diagonally dominant. Yeah, here, definition. Okay, here, diagonally dominant. That means that AII is the entry on the main diagonal line, right? AII. In absolute value, greater than the matrix rho I is AI1. This is rho I of A. Rho I of A is first entry AI1, AI2, and AI minus 1, AI plus 1, and AIN. These are all the entries on row I of matrix A. Diagonally dominant means this entry in absolute value greater than the absolute sum of other entries, greater than AI1 absolute value plus absolute value AI2 plus AI I minus 1 absolute value, and then plus sum over AI I plus 1. This is a row I. If for each I from 1 to n, we have this inequality, then the matrix is called strictly diagonally dominant. Okay. If matrix A is strictly diagonally dominant, then the associate Jacobi method will converge to in this theorem. This theorem guarantee with any initial guess, the iterative scheme converge to some U. But here, this theorem doesn't say anything about U is the solution of the linear system or not. Okay, but here will converge to the solution of the linear system. Okay, guarantee. Okay, with any initial guess. This theorem is convenient to use because I just look at the coefficient matrix, right? Just compare diagonal entry with the other entry on the same row, right? Matrix A is available, so we can check that. We don't need to compute eigenvalues, right? So this is a very convenient theorem. How to prove this theorem? Not difficult. Take a look at my notes. Okay, take a look at my notes. I say for example, let me show you one example about this theorem. About this theorem. Example 1. Consider this linear system. Okay, where matrix A is 4, 1, 0, 1, 0. This linear system have 5 unknowns. 1, 4, 1, 0, 1, 0, 1, 4, 1, 0. From the structure of the coefficient matrix, I can tell this linear system arises from discretization of some differential equation. Okay, by using finite difference scheme. Okay, that we learned. Okay, in one lecture before. Okay, here is 1, 2, 3. Then 1, 0, 1, 4, 1, 0, 1, 0, 1, 4. Yeah. Matrix A. And then right hand side is 1, 2, negative 1. Yeah. 1, 2, negative. Now, from this equation, we derive Jacobi method. Jacobi method. Jacobi method. U k plus 1. Then U T iteration and then C. Okay, where matrix T is 0, 1, 4, 0. Yeah. And 0. This is a 0, negative 1, 4. 0, negative 1, 4. 0. And the vector C. Vector C is 1/2, 1/4. Yeah. Vector C is this vector. Okay. This matrix A, easy to see, is strictly diagonally dominant because take a look, A11 greater than the sum of the absolute values of the remaining entries on row 1. Row 2, 4 is in the diagonal line. 4 greater than the absolute sum of the other entries. So this matrix is strictly diagonally dominant. By theorem, Jacobi method guarantee to converge. In fact, if we starting with arbitrary, okay, say take 0, 0. Starting with the 0, run Jacobi method. After how many iterations? After 20 iterations. 20 iterations. Then the iterate is very close to the solution of the linear system. Okay, very close to the solution of the linear system. But in my notes, I didn't. What is the solution of the linear system? Here. Yeah, very close. Okay. 0.1, 0.7, negative 0.6. Yeah. The solution of the linear system is this. Yeah, 20 iterations. So because A strictly diagonally dominant. Okay, dominant. Yeah, this is topic 1. Second topic, Gauss-Seidel method. It is an improved version of Jacobi. Okay, so to explain Gauss-Seidel, let me write down Jacobi method in full detail. Okay, so I can explain Gauss-Seidel. Topic 2. Topic 2. Jacobi in detail. In detail, okay. This is Jacobi. I write this equation in detail, okay, in detail. Left hand side is U1, the first component. Right side has low U1, okay, low U1. Starting with U2. U2, the second component of this vector, K. Then T13, U3, K, and so on. And then T1N, UN. UN is the last entry of this vector. Then plus vector C, the first entry, C1. Okay, plus C1. Okay, now the second equation, U2, K plus 1, second entry of this vector. This is a T21, U1, K, then plus low U2, because U2 is on the left side, so low U2, but T 23, U3, K, and T 2N, UNK, and then plus C2, second entry of C. Then the third equation, U3, K plus 1. K plus 1, yeah. It is a T31, U1K plus T32, U2K, and then plus low U3, so skip, okay. Then this is a T34, U4K, and so on. 3N, UNK, and then plus C3. Okay, yeah. The last equation is a UN K plus 1, TN1, U1 K. TN3 times U3. U3 K. The last term shouldn't be UN because UN is on the left side. So the last term should be T N N minus 1, UN minus 1. Okay. And then plus CN. Yeah. Yeah, Jacobi method in detail. Okay, take a look at these equations. How to improve Jacobi method? Suppose the iterates converge to some yield, and assume SK is increasing, UK closer and closer to you, closer and closer to you. Okay. And now, first, from the first equation, we compare U1, the first component of the next iterate. Yeah, UK, I call UK the current iterate. Now compute the next iterate. From the first equation, we obtain the first component of the next iterate. After this guy is available, I use it immediately in the following computation because I assume this guy closer to you, then okay, u k plus 1 closer to u1, the first entry of this, then uk 1. Under this assumption, this is more accurate than the current u1k. Okay, so from the first equation, after I get this, I use it in the following computation here. Let me change it. Yeah, k plus 1 here, k plus 1, k plus 1. Okay, yeah. Now I have a new second equation. From the second equation, I compute u2 k plus 1. After I get this, after this guy is available, I use it immediately in the following computation. Yeah, here. K plus 1. K plus 1. K plus 1. Then third equation. After I get this, when this available, I use it immediately in the following computation. Yeah. K plus 1. Yeah. This improvement is Gauss-Seidel. Gauss-Seidel. Okay. Now, it is complicated to write the method in equations. Very complicated, right? Okay, now let me rederive Gauss-Seidel according to the splitting of the matrix A. A is LDU. Okay, yeah, let me rederive Gauss-Seidel. Yeah, here. Gauss-Seidel. Yeah. Gauss-Seidel. Okay, we want to solve this linear system. Now split matrix A into L, strictly lower triangular, plus diagonal, plus strictly upper triangular. Okay. Okay, then plug in this equation into the linear system. We have L D U X is B. From here, I rewrite this equation as LDX plus UX is B. Then move the second term on the right side to the on the left side to the right side. Let me write UX first. Now L plus D, move it to the right hand side. Inverse. Then we have a fixed point equation. Now replace the x on the left by u k plus 1. The right side, the x on the right side by uk. Yeah. This iteration iterative scheme is called Gauss-Seidel. Let me call the different name to the iteration matrix T tilde U. Okay. And this vector plus C tilde. This is Gauss-Seidel. Okay. There are some examples in the looks. Compare Gauss-Seidel with Jacobi. Yes, Gauss-Seidel converge faster because usually T tilde is a spectral radius less than the spectral radius of Jacobi method. So yeah, in general, Gauss-Seidel faster than Jacobi. This is a second topic. Now, third topic, further improve Gauss-Seidel. Okay. The method in third topic is called SOR, successive over relaxation method. Topic 3, SOR. Topic 3, SOR. Okay. Further make improvement on Jacobi and Gauss-Seidel. Okay. Okay. Again, linear system. Okay. And also split A into L D U into LDU. Then we write LDU as L plus alpha times D. What is alpha? Some parameter. Alpha is a number. Okay. What the number is will be determined. L plus alpha D. Then minus alpha minus 1 D minus U. Okay. It is easy to see this equation. Okay. Easy to see this equation. Okay. Then plug in this equation into the linear system and rewrite the resulting linear system as L plus alpha D X equals to alpha minus 1 D minus U X plus B. Yeah. Plug in this equation into the linear system. Okay. Replace the A by this equation. Then rewrite the resulting equation into this equation. Yeah. From here, I divide this equation by alpha. Then we get 1 over alpha L D X. Here, 1 minus 1 over alpha times D. 1 over alpha U times X. Then 1 over alpha B. Then set omega be 1 over alpha. From here we have this equation. Omega L plus D X 1 minus omega D minus omega U X omega B. Move this guy to the right side. Then we have a physics point equation. Omega L D inverse, then times first term. Okay. Then here, omega, this omega times omega L D inverse times B. Yeah. A fixed point equation. Now replace this x by u k plus 1. This x by u k. The resulting iterative scheme is SOR method. SOR method. Yeah. Again, why we name this equation, this scheme SOR? I don't know. I don't know. Okay, I don't know. Yeah. Two special cases when omega is 0. When omega is 0, SOR is easy to see, right? When omega is 0, so this is D inverse times D. Times D. But how about U? D inverse should be Jacobi, right? Omega is 0. No, omega is 0, not Jacobi. Not Jacobi. Okay. Omega is 1. Omega is 1 is SOR is Gauss-Seidel. Gauss-Seidel. Yeah. Yeah. Omega is 1, so L plus D inverse. 1 minus 1 0. So this term is gone. So here negative U. Yeah, exactly. When omega is U, Gauss-Seidel. Gauss-Seidel. Let me name this iteration matrix, give a name according to the book, T omega, depending on omega. And of course, this part, name it C omega, C omega. Now, the question is why we introduce a parameter omega? Because we want to choose omega so that rho T omega as small as possible. When spectral radius smaller, the iterative scheme converges faster. Let me show you one example. Say, take a look at this simple example. Consider a simple example. Say this 2 by 2 matrix. 2 by 2 matrix. 2 by 2 matrix. Yeah. Consider the linear system whose coefficient matrix is this matrix. Then Jacobi. Yeah, from this equation we have Jacobi iteration. Jacobi is iteration matrix. The radius is equal to 0.5. Gauss-Seidel. Gauss-Seidel is a special case of SOR. When omega is 1. Omega is 1. SOR iteration matrix is T omega. Omega now is what is this? Okay. Gauss-Seidel, the rho T1, okay, omega is 1, is equal to what? 0.25. Therefore, if you apply Gauss-Seidel to solve this linear system, much faster than Jacobi, because rho here is a half of the rho of the rho of Jacobi, much faster. Then here I choose omega to be 1. If I choose omega to be a minus 4 square of 3, roughly 1.07, then the SOR method T omega, now omega is T 1.07. The iteration matrix is rho spectral radius is how small? 0.07. Yeah. Actually, 1.07 for this matrix. This is an optimal choice. Make the rho as make the rho smallest. So yeah, if you solve this linear system with SOR method with this choice for rho, converge very fast, super fast. Yeah, but of course, electron question is for a general problem, how to choose omega. How to choose omega? That is a question. Yeah, that is his question. The solution is provided in the PhD dissertation of the order of SOR. But here, I don't want to go into the detail, okay? Here. So for the details, you can take a look at the book. Now, with SOR, I finished, okay, today's class.